Well, thank you, Celeste and Next, for the opportunity to present here in Baltimore. And I want to thank her for introducing the title of my presentation. There are certain learning objectives I'll kind of hit here being a professor. We like to cover hopefully what you take away from the presentation. Professor Carloni did a good job describing FRCM, but we'll delineate the difference between FRCM and FRP. We'll talk about the effects of fatigue and environmental exposure in flexure on FRCM, and in specific the PBO fabric system. And we'll look at the benefits of anchoring systems for FRCM. I think we have another presentation on anchorage systems, but this looks at a couple of different ones. A little bit more background information. So in case you aren't as familiar with it, FRCM stands for Fiber Reinforced Cementitious Matrix, and there you can see the building blocks for the system. Just like in any FRP repair system, we need to do surface preparation, followed by a base mortar, followed by a cementitious mortar, followed by the reinforcing mesh or fabric, and another layer of the FRCM system. And then if you have multiple plies or multiple layers of reinforcement, you would repeat those last two steps again. I like to kind of cover, if you look in the upper right-hand corner here, the guides and standards. This doesn't get into the GFRP code, but for FRP systems for internal concrete, we got the 441R. For external systems, the 442R. And as I said, we've got some new codes being developed that are available now. When we switch over to cementitious type binder systems, as Christian said, we've got the 549 committee, and this is the document that's used for externally bonded FRCM systems. And then there's also one for masonry systems. And so what I'm talking about this morning focuses on the 549 4R document. There's lots of reasons, of course, for repair and strengthening. It could be due to environmental degradation, man-made, natural events, those sorts of things. Or in the case of Missouri, we have lots of structurally deficient bridges in the state, and we've done a lot in that particular area. There's lots of materials in our toolbox to use, and here you can see some of the different forms in terms of bars for internal reinforcement or externally applied systems. And again, the big difference with FRCM is we're using a cementitious binder to match kind of the concrete base material, substrate material, rather than a polymer. And Christian did hit on some of the advantages of these systems. So it has a similar resistance to heat in terms of the substrate being cementitious. There's a little more compatibility of inorganic material for damp substrates, and I'm going to talk about that with the environmental exposure, ease of installation, non-toxic or less toxic than some of the other chemicals that are used for repair systems, and then it is a reversible type system. So in our work, we had actually 5 larger tasks, but I'm going to talk about task 1 and task 5. So this is the fatigue and the environmental exposure, and I will talk a little bit about the anchoring systems on the end. And when we started this work, I really didn't see other work in literature focused on FRCM at that time. So I'll be talking about task 1 and task 5 in the presentation. So we'll jump into fatigue and flexural performance, and our overall objective here was to see if fatigue cycles affected the FRCM system, and then at the same time expose some of these members to different exposure conditions in an environmental chamber and an exterior environment to see what effect that had on the system itself. So kind of the objectives was to evaluate the fatigue resistance and also investigate the durability of the FRCM system. This was our test matrix here. If you look a little bit closer, you can see we had some control specimens. We're just unreinforced without the strengthening system. And then we had specimens in lab condition, environmental cycles, and you'll see the difference between B41 and B51 is the subjection of stress while undergoing environmental cycles. So if you're familiar with typical FRP systems, we usually say there's three things that we have more concerns with, which are usually temperature, moisture, and stress or sustained loading. And those are the three things for a lot of polyurea-based binding systems that we have to be mindful of, T sub G and things like that. So we looked at some similar stuff here. I don't know what's going on there. So I can try to get out of it. Maybe the connection? I guess that came loose a little bit, maybe. Okay. Oh, that's a bummer. Okay. Sorry about that. So that was the conditioning. And we also had variables looking at the number of plies. And you may see we didn't do 2 or 3 plies. The University of Miami did some comparative work, Tony and Annie's group, so we did 1 and 4. And then we also looked at somewhat the effects of frequency. As Christian noted, it's a bilinear material, and you can kind of see what we would expect from testing. One of the things I would mention is that when the cracks form here, you know, when you do these coupon tests, it's probably difficult to get the same layer thickness. Most of the properties are coming from your fibers, of course, but when you install it in the field, do you have the same exact thickness of mortar and those sorts of things in the field? So there's going to be some variability as discussed. In a repair application, we of course have the contribution from the steel, we have the contribution from the fiber, in this case FRCM system, and then of course we can see that we're typically gaining of course an increase in capacity, but also some improvement in post-peak behavior. And as I'll talk about, the anchoring systems is where you can get even better post-peak behavior out of that. So those are kind of things we're interested in, the stiffness, the strength, and the ductility of the system, a lot of times in terms of load displacement behavior. So for our tests, this is a mixed design that was used. When we do these type of tests, we always try to look at the properties of the concrete in the field, of the type structures we would be, an era that we would be strengthening. So we do try to come up with a mixed design, and a lot of the bridges, for example, would be, you know, in the 6,000 to 7,000 range in terms of the concrete properties. But that gives you an idea of the reinforcement that was used, and of course we stay with between the minimum and the maximum reinforcement ratio typically. In terms of the environmental conditioning, this is an 84-day exposure condition, and what we try to accomplish in this is looking at different temperatures, different relative humidities, as well as stress and no stress. And you can see in the upper left figure the spring system that we use to apply sustained loads on the members in the environmental chamber, and then we have some outside. Our DOT, when asked how long would you like to extend the service life of a load-posted bridge, would say, hey, if we can get another 10 to 20 years out of the structure with a repair system, that would be fantastic. Then we can prioritize and schedule for any type of replacement if it's in really bad shape. And so that's what we tried to develop this exposure condition on, that time frame in the Midwest United States, just to give you an idea. This is the actual fatigue testing, and it shows you the load we tried to get to at the service level after repair and strengthening. And then also you can see here that during the first few cycles, you don't necessarily see a lot of loss in stiffness of the system. And this shows you that a little bit better. The blue color is the control specimen The orange color is the unloaded lab, and then you go down with the environmental without stress, the environmental chamber with stress, and then the exterior one. What we do see here is for this one-ply system, we see an initial loss in stiffness of a little bit, and then it pretty much stabilizes. So you can see that fatigue really was not a concern, and none of these, after 2 million cycles, we didn't have any failures or anything like that. That's where we have the stiffness. Now, in terms of the 4-ply system, so we're going from a lower reinforcement ratio to a higher one. We did see, of course, a similar behavior, some initial loss in stiffness, then stabilization. All of them reached 2 million cycles except for the control unstrengthened beam at this higher service level loading with 4-ply system. That one actually failed during fatigue testing. So that's without the FRCM system. And as validation that the repair system is working, this has the strain gauges on it for both the steel and the FRCM, and you can see based upon the measured strain reading, both systems are working. And I'm going to pick up the pace here a little bit. Now, I want to show you for 1-ply and 4-ply systems, we had different failure modes. So for the lower reinforcement ratio of 1-ply, we actually have fiber slippage in the system. And the blue line is the control specimen without strengthening. So we see in all of the cases that we actually increase the load carrying capacity, which is great. But one thing that pops out that's different about cementitious systems is the exposure to moisture in the environmental chamber actually improved the strength capacity, and it also improved the post-peak behavior. That's the green line. So in the case if I did a epoxy-based system, we would usually see a decrease in strength due to deterioration in the resin system. So this is one bonus, I guess you'd say, of a cementitious system. The other thing, when we go to 4 plies, just like with the FRP system, if we have multiple plies, we don't double, triple, or quadruple the capacity, right? It becomes even more critical in terms of the bond performance. And so 1 and 2 plies, you actually get a fiber slippage failure, but when you get up into 3 and 4 plies, the failure mode shifts to a debonding failure. When compared to the ACI 549, all the systems we see increase the load carrying capacity, and in orange, the experimental results provide quite a bit of additional capacity compared to what the standard would predict. So we look good there, 2 to 2.5, 1.3 to 1.6 in terms of a safety factor. So what we see here again is we see a little bit of reduction in stiffness, then it stabilizes, and we saw flexural enhancements in all of those. They were all good for 2 million cycles. The environmental exposure did not affect the beam's failure mode, and the sustained loads in the environmental chamber did reduce the stiffness a little bit. 4 plies, of course, you didn't get 4 times the capacity as we discussed, so it's not necessarily a direct correlation. Now with anchorage, I just want to point out the importance of anchorage. So we looked at a couple of different anchorage systems. One of the anchorage system I'll show you a picture of here, we developed in Raleigh at Missouri S&T, but this was our test setup here. So we looked at the number of layers, either 2 plies or 4 plies, and then we looked at 2 different anchor systems, one without anchors, and then 2 different, a spike anchor and a PBO anchoring system. And sorry about the issues there with the boxes. Okay, yeah, I'm almost finished. So here's the details again of this test specimen for the anchorage system, very similar to what we have. This is the spike anchoring system. So this is on the flexural side on the bottom soffit, and here you can see the steps in terms of preparing the anchoring system. And then here's the newer anchoring system that we developed at Missouri S&T, so this actually uses the PBO system. And of course, there's more labor involved in this, so this is kind of needs to be determined if it's beneficial or not. The one thing I would mention is if you use any of these type of U-wrap type anchoring systems, you do want to get the anchor above the neutral axis so you're in the compression region. That helps lock it in a little bit better. And here's the results. So on the left, the two-ply system. Remember, the blue is the control specimen in this series. And what we see is, irrespective of the anchoring system that you use, you don't really see much difference when you have a fiber slippage type failure. So anchorage is not really effective in a lower reinforcement scenario. However, when we shift over and we're dealing with the case of a higher reinforcement ratio where we get a debonding failure, you can go from no anchoring system in red, and then the spike anchor system in green, and then the U-wrap system that we did with the PBO fabric. So this is where we start to see where the anchoring system becomes effective, and that is in particular when you have the debonding failure. So one takeaway, fiber slippage and debonding, it's important to have a feel for what type of reinforcement ratio you have with the FRCM system to understand what type of anchoring system might work. And this just sort of shows you the debonding on the upper right and then kind of the slippage failure in the middle. You can see really good crack distribution at these higher strain rates, and so that's pretty good. So just to kind of wrap up, you know, you can enhance the capacity anchorage system, but it's important to understand the mode of the failure. And you can see we got 24% more capacity with the U-wrap, 10% more capacity. But in some ways, what's more important is the post-peak behavior and getting a little more ductility out of your system. So these are just some future things that I think we need to look at more in terms of shear performance. We did some work on with and without internal stirrups, transverse reinforcement, had some interesting observations there. There's other anchoring systems that could be looked at, different reinforcement ratios. But I do think we haven't done this in Missouri, but I was hoping to do some type of implementation and monitoring, maybe some load testing, and apply it to some physical structure in terms of the bridge. So these are some of the acknowledgments. Of course, all the fantastic students that I've worked with, and Zena did a lot of work in the middle and received a very nice paper award for some of her work. So thank you for your attention, and if we have time, I'll be happy to take a question.